We're going to do some simple circuit analysis with the circuit we looked at last time. Go ahead and draw our circuit in the phasor domain now. We have our voltage source, 100 at angle 30. Our resistor, 100 ohms. Our impedance of the inductor was J150. And the impedance of our capacitor was minus J50. And these are ohms now. If we were looking at this circuit as if it were all purely resistances and voltage sources back in the DC case, and we wanted to find the current flowing through all three circuit elements and the voltages across all three circuit elements, one of the ways we might do it would be to collapse the circuit down until we had a single equivalent impedance, and then take that impedance and divide it into the voltage and come up with a current using Ohm's law. So let's go ahead and try that. Our voltage source, still 100 at angle 30. But now we have an equivalent impedance, the equivalent, Z sub R plus Z sub L plus Z sub C is equal to 100 plus J100 ohms. So we can find our current phasor using Ohm's law. I phasor is going to be V phasor divided by Z equivalent, or 100 at angle 30 divided by 100 plus J100 ohms. For a current phasor of 0.707 at angle minus 15 degrees. From there, it's easy to go back to the original circuit that we had and say that the voltage that's going to appear across our resistor, V sub R, is just going to be I phasor times the impedance of the resistor, or 0.707 at angle minus 15 degrees times 100 ohms. 70.7 at angle minus 15. Please note that the phase of the voltage and the phase of the current through the resistor are the same. The voltage across the inductor in a similar fashion, I phasor times Z sub L, 0.707 at minus 15 degrees, times the impedance of the inductor, which we said was J150 ohms. If we convert that over into a polar form complex number, that's 150 at angle plus 90 degrees. For a grand total then, the voltage across the inductor should turn out to be 106.05 volts at an angle of 75 degrees. Please note that there is a 90-degree phase shift between the voltage and the current through the inductor. And we see that the voltage phasor is in fact leading the current phasor, as we would expect. The voltage across the capacitor, I phasor, times the impedance of the capacitor, 0.707 at angle minus 15 degrees, times the impedance of the capacitor was minus J50 ohms, and if we convert that over into its polar form, that's 50 at angle minus 90. For a grand total then, the voltage across the capacitor, 5.35 volts at an angle of minus 105 degrees. And here we see that there is again a 90-degree phase shift between the current and the voltage in the capacitor, but we're seeing the current leading the voltage phasor in this case. We can draw our phasor diagram. Here's our voltage across the resistor. Has a length of 70.7. It makes an angle with the real axis of minus 15 degrees. We have the voltage phasor across the inductor, has a length of 106 degree, magnitude of 106, and makes an angle with the real axis of 75 degrees. And finally, we have the voltage across the capacitor at 35. It makes an angle of minus 105 degrees. And then, of course, we have to account for the voltage from our source, which has a length of 100 and makes an angle of 30 degrees with the real axis. I'll leave it as an exercise for the student to take these four vectors and see to it that they do in fact sum to 0. And that's all you need to know about simple circuit analysis with phasors.